The last thing I remember on Wednesday is that someone mentioned that the balance here somehow cannily equals the number of ones in the bit representation of your counter. Do you remember that? Did anyone try to prove it? You did? Okay. Do you have a concise argument you can state in?
Not a very concise argument.
Okay. Okay, go ahead.
So basically, when you ship something from 0 to 1, you just use 1 and you have 1 in credit. So that 1 can be used when the next time you have to shift that from 1 to 0 again.
Right.
And when you have something on the left side of the binary, and you have to shift it to, you have to increment it by 1, तो उसके साथ जो preceding ones हैं वो अब 0 होने वो अपने carry को use कर लेंगे.
Right.
And that one will use the not 2 में से 1 and 1 will be carry and 1 will be used.
Absolutely, absolutely. Yeah, that's the argument, and here's the kind of formal proof of what she just said, that this is the proof by induction. So in the beginning, your counter is at 0. You get 2 credits, and you use only one of them to flip the leftmost or the rightmost bit from 0 to 1, and that saves you one carry, one credit. That credit can be used to turn that 1 into 0 whenever you need it. That's actually the whole point, that you use 1 credit to turn 0 to 1, and you save that 1 credit so you were given 2 credits to do 1 increment. You use one of those credits to turn a 0 to a 1, and you keep that remaining 1 credit for a future flip of that particular bit from 1 to 0, and that's all. Okay, here's the proof by induction. Pretty straightforward, same argument जो मैंने अभी बताया है. Any questions before we move on? आज थोड़ा सा हम ground cover करेंगे. Okay, so stay with me. All right, so one more method for doing this amortized analysis is called potential method. The benefit of potential method is that you don't need to guess the amount of credit that you are going to need. You don't have to guess the amortized analysis. The downside is it's a bit involved, which means कि मैं इसको cover अभी नहीं करने जा रहा. But if you are interested, तो let me know, come to my office hours and we'll discuss it. Maybe towards the end अगर हमारे पास time बचा तो इसकी details में भी हम जाएंगे. Interesting thing is कि थोड़ा सा भी involved amortized analysis, so anything fun requires potential method. उसके बगैर आप कर नहीं सकते. जो हमने जो 2 methods देखेंगे, one was aggregation, the other one was accounting. Both of them are used mostly for toy examples, जैसे हमने binary counter example देखी है. Okay? For example, जो union find data structure है, उसका amortized analysis requires potential method. That's very involved, but in general, any reasonable problem which requires amortized analysis usually requires potential method. Anyhow, slides are there. Go through them. Let me know if there is something that interests you. But none of this is going to be on your exams. Okay. Cool. I wanted to mention this example because this is on your homework for. So dynamic arrays are pretty useful in high-level languages. For example, I think so. For amortized analysis के perspective में Java was probably the first language जिसने dynamic arrays introduce करवाए थे. What it means is that when you are starting an array or a list, you don't specify the size of the list. Okay? So in general C में जो unless you are using vector STL libraries, you have to specify the size before you could declare how many integers you need to store in a list. Dynamic arrays says that you allocate a contiguous chunk of memory without deciding how many numbers you are going to store there. That's a problem, right? Because you are allocating a contiguous chunk of the memory. If you wanted to grow it at a later point, there's a possibility कि जहाँ पे वो chunk आपने allocate किया है, उसके आगे और पीछे वाली space is already used by something else, right? So it's a problem. And the way programming languages implement dynamic array is that they allocate a chunk, and then when they run out of that chunk, they allocate a different chunk somewhere else. They copy the whole array from the first place to the new place, and then keep adding it there. Okay? And when they run out of that chunk, they allocate a new chunk somewhere else, and then copy the whole thing there. So what it requires is two things. First, insert. Insert seems reasonable as long as you don't have to, as long as you are not outgrowing the space that you have. Insert seems like an constant operation. But for example, if you allocated a chunk of size 8 and you already inserted 8 integers there and you are trying to insert the 9th integer, then you are in trouble, because now you are going to have to allocate. Usually what you do is you double the size. So you would allocate an array of 16, and then you would copy the 8 elements from the previous array into the new array, add the 9th element there, right? Now the cost of this insert is not constant. You had to copy n elements from the n or 2 elements from the original array. Well, actually n elements, right? Because the current size of the array is n. You copy the n elements from the previous array, which requires a linear amount of time, which means that insert can at times cost linear, right? For the most part, it's constant, but at times it could cost linear. So worst case analysis would be the linear time, but your task is to figure out how to do its amortized analysis and show that amortized cost per insert is what? Constant, yeah. All right, that's all I'm going to say, but this is a problem on homework. An interesting second problem on the same homework is to design dynamic arrays where you could remove stuff from your array. So let's say you start with an array of size 8, you inserted 8 elements, and then you insert 9th, which means that you allocate 16. Then what you do is you remove the 9th element, 8th, 7th, 6th. Now you have only 5 elements, and you have a space allocated for 16, which seems like an overkill. You should be able to give up that space that you are not using anymore, which means that you're going to have to design a way to first show that amortized analysis of insert is constant, and secondly, that amortized analysis of delete or pop or remove is constant as well. Okay? उसका थोड़ा सा डिज़ाइन आपको करना पड़ेगा. Insert का डिज़ाइन मैंने आपको बता दिया. Insert का डिज़ाइन is simple, that you start with a fixed size, maybe 2 elements, and the moment you are going over it, you're overflowing your current size, you double the size of array and move everything that you had in the previous array to the new one. That's a design for the insert. But how would you design delete? Any thoughts? Yeah.
You can deallocate the memory at that specific point, and when enough memory is deallocated, we can start moving the elements backwards.
Right. So, but the question is, what do you mean by enough? So, insert के case में enough was that you're going overboard. So what you do is you double the array, right? When would you delete?
Like 30% to 50%.
It makes sense, but the 50% will not work. Okay, so it's a question for you guys to answer, but 50% will not work. Doubling works, halving will not work for delete. Anyhow, do you have anyone else? There were hands up in the air. All right, okay, let's move on. So that's all I'm going to say about amortized analysis. I think there are मेरे ख्याल में 2-3 questions हैं. Did anyone get a chance to look at homeworks? Homework 4 specifically? There are 2 questions जो मैंने अभी mention किए हैं. Is there any other question on homework 4 regarding amortized analysis? अगर नहीं है तो I'll put some there, but I really like it. Okay. Anyhow, so back to find union. Okay, so find union के case में this is what we have. We know that we can do amortized, pretty much constant inserts find and pretty much constant unions. Okay, but it's not constant theoretically. It's constant practically. Theoretically, this is inverse Ackermann function. The second data structure we need to go through is called priority queues. You guys probably already saw it in your data structures, but here's the problem that it solves. You're managing emergency ward at a hospital, and patients come at unpredictable times, and they have a severity score. Okay, so you're interested in serving the highest priority patient with the highest severity. What is required is insert. You want to insert a new patient with a priority, whatever priority you assign to that patient. What else is required in this case? Pop, right? You served up patient, you need to remove it from the queue. That's called extract max. Okay. You also want to be able to peek max, which is you want to know who is the next person. And there is one more thing. It's called decrease key or increase key is case mein, where you see a patient's condition worsen. So what you do is you put him at the top of the queue or something like this. Okay. So this is a priority queue problem where you solve mainly two things. इनको हम focus करेंगे. One is insert, that you insert a new element with a key जो उसकी priority है, and you want to extract the maximum of them, okay, or the highest key. You can see that कुछ cases में ये minimum would make more sense than maximum as well. Anyhow, so here's the first thing that should come to your mind, that I just keep a list, unsorted. Whenever I have to insert a new key or element, I put it at the end of the array. And whenever I have to do find the maximum, what you have to do is you have to go through the whole list now, okay, to find where's the maximum key. Insert will take constant time because you know your array and you can put it at the end. Extract के लिए आपको पूरी array scan करनी पड़ेगी, which means that this is going to be linear. So inserts are fast, but extractions are slow. Extract मैंने अभी बताया कि you will have to scan the whole array to find the maximum. यहाँ पे एक और technicality भी है, वो ये है कि you have to remove it now as well. If it's a contiguous array, that's a nightmare as well. Okay. Okay. So second obvious choice is sorted arrays. Sorted array के case में insert take time because now you have to, again, contiguous array problem. You have to find out कि कहाँ पे place करना है, which can be done in log n given using binary search and stuff. But अब उसको split करना, वहाँ पे डालना, that's a nightmare. So in general, if you are doing it using linked list or something like that, you can do it in linear time. Extract max is fast now. Okay, you know where extract is, where max is, and you can extract it in constant time. Our goal today is to do both of these, insert and extract max in log n time. The priority queue का एक और नाम binary heap भी है. If you are interested in the maximum guy to be at the top, तो हम इसको max heap कहते हैं. If you are interested in the minimum guy, then it's a min heap. All right. Let's see how to build this and how to implement insert and extract max. Goal again is to do both of these in log n time. A binary heap is a nearly complete, I should say complete binary tree. Nearly मेरे ख्याल में यहाँ पे खाम खा आया हुआ है. Complete binary tree satisfying the heap property. Does anyone remember what's a complete binary tree? I'm just assuming here that you know. So a complete binary tree is a binary tree where, let me write down the definition, where every node has, well actually every level से कर लेते हैं. Every level has maximum nodes except last level. But on last level, all nodes on last level are left aligned. So this is a complete binary tree. Okay? So every level, first, second, third, have the maximum element except the last one. Ab last के ऊपर you will have whatever elements you have, all of them must be to the left. This one is a complete binary tree. This one is not a complete binary tree. Okay? I add an element here, so here this is again a complete binary tree. Are we clear? Okay. So a binary heap is a complete binary tree. I have a picture right there. I didn't have to make the picture. But a binary heap is a complete binary tree where this holds, that node's key or value, if you must, is greater than equal to its children's keys. Okay? So 16 must be more than 14, 10, and so on. If you're interested in max heap, and the other way around if you're interested in min heap. I think the nicest thing about binary heap is the last part, that you don't need a special pointer data structure for this to work. All you could do is put all of these numbers in an array, and it would still look like a binary heap. Since this is a complete binary tree, so its height is limited, it's log n, and max is always at the top. So this array represents this tree, which is nice, right? You don't have to deal with any pointers. Everything is just in a contiguous array. Okay, so if I want to find out, for example, 14th right child, how do I do it? So 14 has two children, left one and the right one. How would I find the right child of 14? How do I find 7? If I have to go, for example, 14 to 7, how do I do it? Yep.
I think it's like the index of 14 multiplied by 2 plus I plus 1, sorry.
Yeah, absolutely. That's what it is. So left child is 2 times the index of 14, so it's at 4. And the right child is 2 times 2 plus 1. And the parent is basically divided by 2. और उसका float लेना है आपने. All right. Again, assuming that you have seen already this in your data structure, I'm keeping my pace. How do we insert this? This is how we insert it. We add x at the end. So for example, if I'm adding 15 to this array, what you do is you add 15 at the end, and then you sift it up to make sure that heap property is maintained. So what you do is you compare 15 with its parent. If it is violating the heap property, which is that the parent must be greater than its children, so here you replace, you swap them. Okay? So in this case, this is what happens. 14 comes down and 15 goes up. उसके बाद you try 15 with its parent, which is 16. यहाँ पे heap property destroy नहीं हो रही, so we are okay. And this is it. This is how insert works. This is done in log n time because so you add 15 at the end, and then you sift it up to your tree. The height of the tree is log n, which means that number of comparisons is at most log n. Okay? All right? Okay. So second operation we were interested in called extract max. Our max is already at the top. Okay, so we have to somehow remove the max from the top. So what you do is you swap the top with the last element. जब element आपके पास last में आ गया, all you need to do is make sure कि आपके array का size आप decrease कर दें by 1, तो वो remove हो जाएगा. Okay, so उसके बाद you need to make sure that 7 wherever it goes is not violating the heap property, which is that the parent must be larger than its children. So what you do is you sift down, I guess. Yeah. Okay. So अभी हमने 16 को remove कर दिया. We need to compare 7 with 14 and 10. इन तीनों में से जो maximum होगा, which that's gonna be replaced with 7, and 7 उसकी जगह पे आ जाएगा. So 14 and 7 are swapped. उसके बाद I'm gonna compare 7 with its children. or 8 or 7. I was trying to make curved arrows here, जो यहाँ पे नहीं बने. पिछली slide पे curved थे ना? यहाँ पे curved है. Bend नहीं किया होगा. Okay. Anyhow, so that's how you do extract max. Okay. Again, all you're doing is you are sifting from top to bottom now, which means the number of swaps or comparisons is the height of the tree, which is log n.
Isn't the number of comparisons more because at higher level to be we are comparing it with 2 instead
We are comparing it with 2. We are finding out the maximum of these 3 numbers. Yes. So the number of comparisons is, if you must, 2 times log n. Yes. Yeah. But it's still asymptotic log n, so we are okay. Yeah. Swapping is, yeah, number of swaps is log n. Yeah. Bolo?
Sir, why don't we take हम root node को हटाएं and just make one of its children the next root node at hand? Like directly 14 या 10 कोई.
Right. उस केस में होगा ये कि 14 will have more children now. 14 will have 8 and 7 again, और फिर 10 भी उसका child बन जाएगा. We don't want, right? We just want to keep this binary. We want everyone to have 2 children. वो destroy हो जाएगा. Again, उसके भी tricks हैं. फिर swapping करनी पड़ेगी आपको. Keep one of them. Essentially, जो हम अभी कर रहे हैं वही आपको करना पड़ेगा. This seems like the clearest or cleanest way to do it. All right. Cool. Build heap is another operation that we have at times. At times we need to do it. Naive approach is that you start with an empty heap and then you insert one element at a time. Insertion takes log n time, which means that inserting n elements would take order n log n time. But we can somehow do this in order n time by doing this. So you start with the array, which is completely arbitrary. उसके ऊपर कोई heap property नहीं है. And then what you do is you sift down from I is equal to n over 2 से लेके 1 तक. Okay. ये वाला जो algorithm है, I want you guys to kind of appreciate it. Even if you have seen it before in your data structures class, I think यहाँ पे एक आधा point है जो अक्सर miss हो जाता है. Okay. So first of all, why? So ये क्या कह रहा है? Sift down ये make sure कह रहा है कि the tree starting at I is a valid max heap. Okay. So if I am doing sift down at this point, I'm making sure कि ये वाला जो tree है, this is a valid heap. Okay. And I'm starting it at n over 2, say, and I'm going up to 1. Okay. A naive way to do this is to do this for, let's see this, right? For I is equal to n to 1, right? मेरा नहीं ख्याल कोई फ़र्क पड़ेगा उससे, but we don't need to sift down the last n over 2 elements. And why is that? बोलो क्या? The last n over 2 elements in a complete binary tree are leaf nodes. They don't have any children, which means that they are already valid max heaps or min heaps if you want. So do we agree that this will ultimately create a valid max heap? Yes, no? So what I'm doing here is that I'm making sure, so I'm starting here, making sure कि ये वाला जो tree है, this is a valid max heap. उसके बाद I'm making sure कि ये वाला जो tree है, it's a valid max heap. उसके बाद I'm doing this for this, उसके बाद I'm doing this for this one, and lastly I'm doing it for this one. Is that enough? Is this correct? Yes, no? Either a yes or a no would do. Bolo? Yes? 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 Okay. 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 Bolo? Bolo? What's funny? Bolo? क्या हुआ है हंस क्यों रहे हो आगे आ जाओ If you have a joke, we really need a joke at this point. Okay, अब बताओ yes, no?
Yes.
Okay. Any no's? Anyone has a no? All right. Then I have a question for you. Okay. Why don't I just call sift down in the top here instead of starting it? मैं अब I don't know n over 2 times sift down कर रहा हूँ ना यहाँ पे यहाँ पे यहाँ पे यहाँ पे. All I need to make sure है कि जो whole tree है ये एक binary heap बन जाए, right? Why don't I just call it at that root? Would it make a binary heap, complete binary heap? Complete binary tree, which is a max heap. क्या?
Would only sort a single branch. Wouldn't explore all the branches.
Right, right. So that's fundamental concept is what sift down does it. It makes sure that a given node is correctly placed in the binary heap. Okay, so it will make sure that this root goes to where it must. It won't make sure, for example, if this ends up being swept with this one, so ये वाले tree will not necessarily be a max heap or a min heap. Okay, so we need to make sure that all of the sub trees are already valid max heaps before I do it on the root. All right. Cool. So instead of doing in n log n time, the goal is to make sure that this is doable in linear time. And how do we do this? So here's the key insight. So sift down को अभी मैंने कहा था it takes log n time. Sift down takes log n time when the height of the tree is log n. Okay? Which means that actual cost of sift down is the height of the tree जिसके ऊपर मैं ये काम कर रहा हूँ. So the observation is that most of the time I'm doing sift down on smaller trees. जब यहाँ पे कर रहा हूँ तो sift down is being done on a tree of height 1. और जब यहाँ पे कर रहा हूँ तो sift down is being done on a height of tree 2, and so on. Okay, this observation gives you what you're looking for, which is the linear time complexity. So leaves के लिए आपको कोई काम करने की ज़रूरत नहीं है. जब आपकी height 1 है उसके ऊपर you have to do one sift down, one height sift down. Probably this C here is probably 2. 2 comparisons आपको शायद करने पड़ेंगे. 2 के केस में you will have to do 4 comparisons. But here is another observation, which is that the number of leaves is n over 2. If you remove the leaves, the remaining leaves is n over 4. If you remove those, the remaining leaves is n over 8, and so on. Which means that number of nodes at height 0 is n over 2. Number of nodes at height 1 is n over 4. Number of nodes at height 3 is n over 16, and so on. Okay, so I'm doing a lot more work a lot more shift downs for smaller heighted trees and very few shift downs for larger heighted trees, which gives me this formula that I sum it over all possible heights 0 to log n, and my number of trees with this height is n over 2 to the power h plus 1. Okay? So for 0 it's n over 2, for 1 it's n over 4, for 2 it's n over 8, and so on. And this is the cost, which is a constant times the height. So I'm going to get Cn over 2 is a constant with respect to h. In the sum, I need to figure out what the sum for which I need a closed form is h over 2 to the power h. ये वाला part clear है? So all I'm saying is that I have to sum up the cost of shift down for all different height trees, and I have to sum it up for all heights. And for a given height, I have n over 2 to the power h plus 1 different trees. What is this sum? So we have seen this sums, right? We have seen this I is equal to 0 to n sum of I. ये चीज़ हमने देखी हुई है. इसको मैं h कर देता हूँ just to make it look familiar, right? This we know, right? ये वाला sum हमें पता है. Yes, no? Do we know this sum? People who know this sum? Sum of numbers from 1 to n? 0 to n or n to n, 1 to n. Okay. Yes? Okay. There are people who don't know the sum of numbers from 1 to 100. Okay. This is simple, right? This is so 1 to till 100, 99 कर लो यहाँ पे, and then you write it twice, 99 to 1. So this is 2 times the sum of this thing, right? So, but sum of individual columns is 101. So this is this many, n plus 1. And how many do I have? N of them over 2. Right? So it's n into n plus 1 over 2. अच्छा, दूसरा sum है h goes from 1 or 0 to n 1 over 2's power h. ये भी हमने देखा. We saw this last week, है ना? Yes, no? Did we see it last week? I think we did it last week, or did, I don't know, I was making this square and there were people shouting, why are you doing it with square and not doing it with geometric series, है ना? तो ये हमने conclude किया था कि this ends up being equal to 1. 0 से start करेंगे तो this ends up with equal to 2, है ना? We saw this, है ना? We didn't do it? We definitely did it. I know people coming up to me saying कि ये ऐसे क्यों कर रहे हैं, हम geometric series से क्यों नहीं किया? So anyhow, इसको अगर I don't know देखना चाहते हैं तो this is 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 and so on. We did it for infinite sums. Okay, sorry. We did it for infinite sums. We did not do it for finite sums, which means that for finite sums, this is less than or equal to 1. Right? So this is a square of 1 by 1 area. 1 over 2 covers half of it. 1 over 4 covers half of that, and so on. What's going on? Who is calling me? Okay. I should have, है ना? अच्छा, slides कहाँ गई हैं मेरी? Okay. खैर, okay, the point I was making is कि हमने ये वाला sum नहीं देखा. Okay? This is it possible? I turned off the internet, did I not? वाईफाई ऑफ है, ये कैसे कर रहा है इसको ऐसे? Some weird black magic going on here. Okay, so ये हमें नहीं पता what this is, है ना? How do we do this? How do we figure out what this is? This is a cute trick. मेरे ख्याल में if you, आज की क्लास से अगर ये वाला ट्रिक आप सीख लें तो I would be okay. You would probably not be okay because there's हाँ बोलो. Okay, let me try to figure out what you're saying. Sorry. बोलो. S minus half S. So S is basically this thing, है ना? It's h over 2 raised to power h. I don't care कि कहाँ से start हो रहा है और कहाँ जा रहा है, but let's say it goes from 0 to n. Okay? तो k लिख देता हूँ क्योंकि confusing हो जाएगा. वहाँ पे n means something else. Okay, so what do I do? इसको expand करो. This turns out to be 0 और उसके बाद this would be 1 over 2 plus 2 over 4 plus 3 over 8 plus 4 over 16 plus 5 over 32 and so on. Okay. इसमें से अब हमने s over 2 देखने के क्या चीज़ है. So s over 2 would be 1. I understand जिस तरफ आप जा रहे हैं that will not work, but let's see. So 1 over sorry ये क्या हो जाएगा? ये 1 हो जाएगा है ना? I'm dividing it by 2. 2 over 8, 1 over 4 हो जाएगा. और उसके बाद 3 over 16 हो जाएगा, 4 over 32 हो जाएगा और 5 over 64 हो जाएगा and so on. Okay? पहली टर्म 1 नहीं हुई, 1 over 4 होगी है ना? दूसरी 1 over 8 होगी, 2 over 8 होगी बेसिकली, राइट? Okay. No. So you would be left with 1 over 4 plus 2 over 8, right? Plus 3 over 16 plus 4 over 32. This is s minus s over 2. 1 over 4 होगी. 1 over 2 is 1 over 4 निकालेंगे तो you'll get 1 over. क्या करूं s? ओह अच्छा आप ये कह रहे हैं. Okay, so okay, good. Let's try. So you end up with 1 over 2 and you get 1 over 4 and you get 1 over 8 and you get 1 over 6. This works, right? 1 over 32 and the last term you end up with is 1 over वो यहाँ पे होगी है ना? k over 2 raised to power k plus 1 नेगेटिव का है ना? Is it true? Right. मैंने ये क्यों नहीं किया? This looks much easier than what I was doing. There must be something wrong with it. Let's see. Does everyone agree with this कि ये ठीक है? या किसी और के उसमें है? Let me just make sure. Okay. So मैंने तो आधा घंटा लगाया यार इस पे. मैं तो ये क्यों नहीं किया? Make sure कि कुछ गलत ना हो यहाँ पे. I need to. हाफ से मल्टीप्लाइंग योर टेलीस्कोप कर रही हो उसको, वो इधर आ जाएगा और एक निकल जाएगा. This makes sense to me. So this is s over 2, or 2 times this is s, or 2 times s is less than or equal to 2. Nice, nice, good. Yeah. Really nice. Good, awesome. I don't have a frisbee. You deserve a frisbee. Bas kar lo. Okay. Let's see how I did it. Okay, the monster way I did it. Okay, so. So this is what I did. So this is the geometric series, infinite geometric series of x to power h, and you get 1 over 1 minus x. You differentiate it with respect to x, and you get h out now. And this is h times x to the power h minus 1, which is 1 over 1 minus x squared. And that's what we were looking for, right? You multiply this with h and you get what you were looking for, and this is equal to x over 1 minus x squared. Ab isme, if you put x is equal to 1 over 2, you get s, and that's what the geometric series is. Okay? Cool, but this one is much cooler. But all of this comes out to mean that priority queue ki jo build heap ki cost hai, that's linear. That's not n log n. Okay? All of these sift downs cost at most linear time. Okay, skipping this because iske upar humne baad mein wapas aana hai. I'm gonna skip this as well. Nice example, देख लीजिएगा इसको. This is an application of priority queue जो मेरे ख्याल में आप लोगों को पता होनी चाहिए. Okay, so heap sort uses priority queue to sort n elements, and what it does is it builds a heap, और heap को build करने के बाद it this is not a यहाँ पे कुछ गलत हुआ है. Okay, so you build heap in linear time, and then what you do is you remove the maximum element n times, and you would get a sorted array, right? So you start with an array which is this. उसके बाद you do a build heap which gives you a heap. उसके बाद in the first pass you remove you do max heap, which means कि 1 और 16 would be swapped. 16 सबसे end में चला जाएगा. उसके बाद you would do the same with the 14 and so on. Or after doing n extract max, you are left with sorted array. And all of this is being done in the same space, so it's in space sorting algorithm. Its time complexity is n log n worst case, and it's in place like quicksort. So we have best of the both worlds, but in practice it turns out to be a bit slower, even compared to quicksort and both merge sort. Okay. All right, so we have learned two data structures, union, find, and priority queues, which means I can quickly, in the next 5 minutes, introduce minimum spanning trees. So this is what we talked about. We are given a graph, and we want to find out a tree whose total sum of weights is minimum possible. This one, okay? And here's the definition. So we have a graph and we have a weight function, and we are interested in subset of edges. We want these edges to be spanning all vertices, so everything must be connected. There should not be any cycles, and the total weight should be minimum over all possible trees. यहाँ पे मैंने weights पे r plus लिखा हुआ है, this is not necessary. यहाँ पे गलत लिखा हुआ है, it should be r. I don't care कि weights उसके positive हैं या negative हैं. Alright, so ये हमने last time try किया था to try all possible subsets of edges. This turns out to be exponential, so we want a better method. Before we study Kruskal's, there are a few facts वो हम आज कर लेते हैं, and Kruskal's and Prim's will do it on Wednesday. Okay, so first fact is that if you add an edge to a tree, you will always create a cycle. Okay, so ट्री के अंदर एक canonical property है, वो ये है कि between every pair of vertices there is a unique path in a tree. Okay, so if you add an edge between A to D, what it means is that you are adding a new path from A to D, and if there are two paths from A to D, then there is a cycle. Okay, so whenever you add an edge to a tree, you are creating a cycle. उसका converse is कि if you have a cycle and you remove an edge from that cycle, your graph would still be connected, which means कि उसके अंदर एक path exist करेगा. Third fact is that if you remove an edge from a tree, then the tree will become disconnected. Right? Again, based on the same fact that there is a unique path between every pair of vertices in a tree. Okay? This is the last slide for today, and this is very important for at least two algorithms जो minimum spanning tree के ऊपर based हैं, but a lot more. Okay, so what's a cut? A cut is partitioning of vertices into two sets and non-empty, and we say that an edge crosses a cut if it goes from a vertex in the first part to a vertex in the next part. Okay, so we make a couple of examples. So let's say you start with the graph like this. One, two, 5, 7. So this is a cut. So I'm going to move some of the vertices in S, and everything else is in the second part. And the edges 2, 4 and 3, 5 are the cut edges. Okay? But more importantly, a cut could be any subset of vertices. So S is equal to 1, and the second part is V minus S is also a cut. Okay? Here is a question. I have a complete graph on 4 vertices. How many cuts can I have in this graph? मैंने भी काउंट करने हैं वैसे. क्या? 3. Oh, definitely more than 3. So एक distinction है जो मैं clear कर देता हूँ. So S, V minus S and V minus S and S is the same cut. Okay. So 1 S के अंदर आप 1 रख लें या आप S के अंदर 2, 3, 4 रख लें. This is the same cut. Okay, how many cuts can I have in this graph? Six. Let me just make sure. Close. Close, yeah. 7. This thing has 7 cuts, I think. इसी एग्जाम्पल को एक्सटेंड कर लेते हैं. Just to make sure that you understand what's going on. How about this one? Number of cuts in this graph. Yes. So why are you saying why we have 7 cuts there? Okay. मैं आपको ये बता दूं फिर आपको ये वाला आंसर क्लियर हो जाएगा. ये वाला so यहाँ पे how many cuts do you have? Yeah, you can separate each of these vertices. So you get 3 cuts. यहाँ पे you get 4 cuts जिसमें you can separate one of the vertices. उसके बाद you can have another cut जिसके अंदर you have 1 3 on one side and 2 4 on the other side. है ना? You can have another cut जिसमें 1 2 is on one side and 3 4 is on the other side. And you have one more cut which is 1 4 and 2 3. है ना? Now can anyone answer this? Yep. No. 15. Yeah. How did you get it? Yeah. So all vertices and the number of subsets of vertices is 2 raised to power n. And अब उसमें से half of the vertices are going to be in S, half of the vertices are going to be in S, and half of them are going to be in V minus S. Okay, which means half of that, 16. One of those cuts has an empty set in S, so you discount that. So it's 2 raised to power n minus 1 minus 1. Okay. All right, that's it. We'll move on from this slide onward on Wednesday.